Children, now we are going to discuss about one of the important property of halogens, oxidation ability. Nothing but oxidizing power. Here, under the periodic table, here halogens are high oxidizing power due to high electron gain enthalpy. Therefore, the order of oxidation ability fluorine, chlorine, bromine, iodine. Even though chlorine is high electron gain enthalpy, but fluorine is the high oxidizing power. Yeah, due to reasons are about. One of the reasons is as per standard electrode potential values in the reduction form. Here, fluorine is the highest standard electrode potential value. So you know, higher the standard electrode potential value, higher the oxidizing power. So always the electrode potential, standard electrode potential values is directly proportional to oxidizing power. When comparison of here electrode potential values, fluorine is the highest value. That is why fluorine is the high oxidizing power compared to chlorine. Even though chlorine is high electron gain enthalpy. You see, due to high oxidizing power of chlorine, what happened here? Fluorine oxidizes all the halides from their corresponding salts into corresponding halogens. That is the main cause here. Due to high oxidizing power of fluorine, it oxidizes chlorides to chlorine. Here, potassium chloride, chlorine oxidation state is -1. Here, chlorine oxidation state is 0. What happened? Chloride ion oxidizes to chlorine. Like fluorine, here oxidizes to bromides to bromine, iodides to iodine also by chlorine. Here, chlorine oxidizes only bromides to bromine as well as iodides to iodine. Bromine oxidizes only iodides to iodine only. But iodine, it cannot be oxidized by any other halides of the corresponding salts. Why? Because iodine is the weak oxidizing agent. Understand, children? Observe here, in down the group, here higher halogens means higher electron. Here, high electronegativity of the halogens or the small size of halogen atom always here displaces the higher size of the halide ion from the corresponding salts. That is the conclusion, children. What happens here? Small halogen atom displaces the larger halide ion from the corresponding salts. See example, children. Fluorine is a small size. Here displaces of large size of chlorine, that is halide ion from the salts. Like chlorine displaces bromide ion, bromine displaces iodide ion. Understand, children? But iodine does not displaces the bromides, but not displaces the chlorides. Like that, bromine does not displaces the chlorides. Chlorine does not displaces the fluorides. Why? Because always the small size of halogens displaces the large size of halogen atoms from the corresponding salts. That is the polymer reaction. Next, due to high oxidizing power of fluorine, chlorine and bromine, here oxidizes aqueous solution of ferrous ions to ferric ions. Ferrous ion converted to ferric ion in aqueous solution by fluorine, chlorine, bromine only, but not iodine. Why? Because iodine is a weak oxidizing agent, children. So that's why iodine cannot remove the electron from ferrous ion due to weak oxidizing agents. Next, here the main reasons are here halogens are high electrode potential values. That is the cause for strong oxidizing agents or strong oxidants. That is why here electrode potential values are always directly proportional to oxidizing power, children. Next, here the oxidizing power also explains with the help of net enthalpy. Here before explain oxidizing power with the help of electrode potential values. Also to explain oxidation ability with the help of enthalpy change also. Because In halogens, some elements are expressed in the gaseous state, some are liquid state, some are solid state also. Like fluorine, chlorines are gases, bromine liquid, iodine solid. But how do you calculate the net enthalpy for each halogen? Generally, you can take here. Suppose the halogen is present in the solid state, like iodine. Here the solid halogen converted to liquid halogen. But what happens solid to liquid means? You are melting. That is called your fusion also. That's why in this process involving of the heat is called enthalpy of the fusion. That is taken as delta H1. But some elements that exist in the liquid state. Suppose a liquid state example bromine. The bromine liquid here converted to gaseous state. That is called here what happened? Liquid to gas means so vaporization. In this case here also heat is required. That is called enthalpy of vaporization. How much amount of heat required for the conversion of liquid to gas. That is called enthalpy of evaporation. So then, some are in gaseous state only, like fluorine and chlorine. So now the chlorine, fluorine gaseous molecules converted into atoms. That is atom. Molecule to atom means dissociation. That's why in this required also energy, not heat. That is called enthalpy of dissociation. Next, after the formation of atom, it is not stable. Then ion only stable. That's why this gaseous atom gain of electron, then converted to gaseous ion. This is a stable ion. Here gain of electron means electron gain enthalpy. That is why here also electron gain enthalpy value. Next, here the formation of gaseous ion in aqueous solution is converted to hydration ion. So here also heat is liberated. In this case also enthalpy of hydration. Children observe here delta H1, delta H2, delta H3. Up to these three values are always endothermic process because heat required either fusion or vaporization or dissociation. But in this case of delta H4 and delta H5 what happened? Heat liberated. Electron gain enthalpy is a exothermic process. Like that. Enthalpy of hydration is also exothermic process. So, your calculate your values are determined by experimentally. By these values can be calculated to get the net enthalpy value. Therefore, net enthalpy, first one is your molecular state. You can find the atom delta H1 by 2. Next here. Second one, molecular state delta H2 by 2. Third one, also delta 2 molecules are there, 2 atoms are there. That's why you can take one atom, delta H3 by 2. But here observed here, delta H4 and delta H5, only single atom. Delta H4 plus delta H5. Then you will get the net enthalpy value. If the net enthalpy value is more negative, it becomes the best oxidizing power. So that's why to calculate the every element net enthalpy values, to observe the values with the help of net enthalpy values to determine the oxidizing power also. So therefore, your fluorine is the highest negative enthalpy, net enthalpy value. So that's why here fluorine is acts as a best oxidizing agent. Why? Because here fluorine is a low bond dissociation enthalpy, high hydration enthalpy. Fluorine, low bond dissociation enthalpy, high hydration enthalpy. That is why the net enthalpy value is a high negative value. That is why higher the negative value of the net enthalpy behaves as a best oxidant. So that is useful for to explain the oxidation ability with the help of net enthalpy values also children. So, in the final conclusion, the oxidation ability explains with the help of standard electrode potential values as well as net enthalpy values. Higher the electrode potential value acts as a good oxidizing agent. Like that, higher the negative net enthalpy value also acts as a good oxidizing agents. So the final conclusion results either net enthalpy values or with respect to standard electrode potential values, fluorine is the highest values. That's why fluorine is considered as best oxidizing agent children. So that is the property of your oxidation ability property. Now children, your action with the hydrogens. Here halogens reacts with the hydrogen. The formation of the compounds are called hydrogen halides. The general formula of hydrogen halides are HX, where X is called fluorine, chlorine, bromine and iodine. Therefore, the formation of the corresponding hydrogen halides are HF, HCl, HBr, HI. That is called hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide. Now we will discuss about some of the properties of corresponding hydrogen halides. So now, first property, what is the condition for the reaction? Here the reaction takes place in between hydrogen and fluorine, even in the dark place also. In between hydrogen and fluorine, the reaction takes place even in the dark place also. Why? Because fluorine is a high reactivity. That's why H2 reacts with F2 to form hydrogen fluoride. But here in between hydrogen and chlorine, the reactivity is less. That's why in between hydrogen and chlorine, the reaction takes place only in the presence of sunlight. But in the dark place, very slow reaction. So, but to speed up the reaction, you need for some catalyst. Generally, using the catalyst is platinum catalyst. Therefore, in the presence of sunlight as well as catalyst, the reaction becomes very fast between H2 and Cl2, then form the hydrochloric acid. Otherwise, in absence of catalyst, in dark place, the reaction is very slow. That is why here in between hydrogen and chlorine, the reaction takes place in the presence of sunlight. Like here in between hydrogen and bromine, the reaction takes place catalyst as well as the heat also required. That is using here about 590 Kelvin temperature. Then what happened here? The reaction takes place between hydrogen and bromine to form the hydrogen bromide. But the formation of HA is very difficult. That is why you need for very high temperature around 710 kelvins or in the presence of and also need for catalyst platinum. Only even though the reaction between hydrogen and chlorine is a reversible reaction, children. That is why here H2 plus I know the formation of hydrogen iodide is HI in the reversible reaction. But other halogens H2 plus here H2 plus halogens gives rise to 2HX. It is a irreversible reaction. But whereas hydrogen reacts with iodine, the formation of hydrogen iodide is unstable. That's why I come back again also. So, what understand here? Here in between hydrogen and halogens, the reactivity go down, decreases. Understand that? So that's why here the formation of HF is very easily as well as the most stable also. The stability also what happened? Decreases. That's why HI is unstable and again backward reaction also takes place. That is why the preparation of HI is also very difficult. But the preparation of HF is very easy and also is the most stable also. That is the reaction condition in the preparation of your hydrogen halides. Next one about the bond length between hydrogen and halogen. You know, the size of the atom increases from fluorine to iodine. The bond length also increases between hydrogen and halogen. That's why here the bond lengths are increased from what happened here? HR, next to HCl, next to HBr and HI. This is order of bond lengths. Next children, bond enthalpy between HX. And here HF is the most stable. That's why the dissociation of HF molecule requires high bond enthalpy. Therefore, observe here bond enthalpy values are what happened? Gradually decreases. This is order of bond enthalpy children. HBr, HI. This is order of bond enthalpies. So highest bond enthalpy is HF molecule because of it is the most stable. Next, melting points. Observe here, the melting point of HF is low when compared to HI. Therefore, the order of melting points, HCl is the lowest, next HBr, next HF. but HI is the highest. But expect us, here HF is the lowest, but not HF is the lowest. When compared to HCl and HBr, it is highest. Why? Because HF molecule forms the hydrogen bonds. Intermolecular hydrogen bonds are exhibits. That's why it is a high melting point when compared to HCl and HBr children. So therefore, here the order of your melting points. Next, like that, boiling points also, there is slight variation. HCl and HBr, lowest boiling point. Even comparison of HF and HI, HF is more boiling point than HI. Therefore, in hydrogen halides, which is highest boiling point, HF is the highest boiling point. So, due to here also reason, hydrogen bond formation. And children, here observe here, boiling point is always this one. Always the boiling point is quite opposite to the volatile nature. That means here HCl is more volatile nature, but HF is least volatile nature. Sometimes asking which is more volatile nature or which is less volatile nature. That is quite opposite to boiling point. Irrespective of any hydrogen halides, not only 17th group elements like 16th group or 15th group like that. So that is why the boiling point and the volatile natures are inversely proportional. Next becomes stability. Already discussed here children, which is the most stable hydrogen halide. HF is the most stable hydrogen halide. Next pKa values. Here the pKa values is observed here. HF is the highest pKa. So the pKa, with the help of pKa values to explain the acidic nature. Higher the pKa value, lower the acidic nature. So always the pKa and acidic natures are inversely proportional. So here HF is high pKa value. That becomes it is a weak acid. But HI is the lowest pKa value. It becomes a strong acid. Understand children? So HI is the strongest acid, but HF is the weakest acid. With the help of pKa values. Next, reduction ability. You know, fluorine is the strongest oxidizing agent. Like that, HF is a not acts as a reduction agent. Here, only chlorine, bromine, and HCl, HBr, and HI are acts as the reductants or reducing agents, but not HF acts as the reducing agent. Okay, so what happened? The reduction ability or reducing power gradually increases from HF to HI. So that is why HI is a strong reducing agent, weak oxidizing agents. So here also comparison, here reducing agents and oxidizing power are inversely proportional. That is why HF is the strongest oxidizing agent, but HI is the strongest reducing agent. Now children, we want to discuss about the action with oxygen. Here halogens reacts with oxygen to form many oxides, but most of them oxides are unstable. So especially here the fluorine formation of the oxides are OF2, O2F2. OF2 is called oxygen dichloride. O2F2 is called oxygen monochloride, but exhibits as the dimer state. So the formula representation is the dimer form O2F2, but monomer form OF4. Understand that? Next here, the most stable oxygen fluorides are oxygen dichloride at 298 Kelvin. Nothing but at room temperature, which is the stable form. Oxygen dichloride is the stable form. Next here, the higher oxides of halogens tend to more stable than lower oxides. Here the same element to form various oxides. That means here higher oxidation states of the oxides are more stable. Observe here, chlorine form various oxides. Chlorine monoxide, dioxide, trioxide, heptoxides. Your oxide state is chlorine +1, your chlorine oxide state is +2, your chlorine oxide state is +3, but your chlorine oxide state is +7. Then what happens here? Oxide state increases. That's why the stability of the oxides also increases. Covalent nature also increases. Acidic nature also increases with respect to oxidation number. Okay, children. Next, O2F2. Here oxygen monochloride, it oxidizes plutonium to plutonium hexafluoride. Plutonium to plutonium hexafluoride. That only the removal of the plutonium in the spent nuclear fuels, you are using of the O2F2. How to remove of the plutonium? By the formation of plutonium hexafluoride. So in this case, you are using of O2F2 compound for the removal of excess of plutonium in the nuclear spent nuclear fuels. Next one, chlorine oxides. These chlorine oxides are highly reactive and oxidizing agents and tend to explosive nature also children. Chlorine oxides. And especially chlorine dioxide is used as a bleaching agent in paper industries, textile industries, as well as in water treatment purpose also using the chlorine dioxide. Like the children, bromine oxides, Br2O, BrO2, Br2O3, bromine monoxide, dioxide. But these bromine oxides are unstable children, are very lowest stability. Whereas iodine oxides, iodine tetroxide, iodine pentoxide, iodine heptoxide. So here, these all are solids, insoluble solids. But heat here decomposes on heating. Therefore, and stability is also less stability, but are on heating easily decomposes. And also these are acts as a good oxidizing agents. And especially I2O5 acts as a good oxidizing agent. And it is especially used for the estimation of carbon monoxide. So in estimation method, here I2O5 is used for estimation of the carbon monoxide level. So these are the properties of oxides. Then halogens reacts with oxygen. So now children, action with metals. Here halogens reacts with metals. The formation of the compounds are called metal halides. So some examples are given. Magnesium, aluminum reacts with the halogens to form the corresponding halides like magnesium bromide, aluminum chloride, like that. Some metals here exhibits the more than one oxidation state. In more than one oxidation state means so in this case here always higher oxidation states of the compounds are more covalent nature. So for example we can take here copper exhibits +1 and +2, like iron +2 and +3, like tin +2 and +4. So like that what happened here oxidation states in cuprous chloride here oxidation state of copper is +1. In cupric chloride oxidation state of chlorine is +2. So that is why cuprous and cupric chloride which is more covalent? Cupric chloride is more covalent. Like ferrous chloride and ferric chloride which is more covalent? Ferric chloride. Stannous chloride and stannic chloride which is more covalent? Stannic chloride. Like that. Uranium tetrachloride and uranium hexachloride which is more covalent? Uranium hexachloride. So that is why they are increasing the oxidation number, yet the covalent nature is increases in metal halides. And also here these are most of the metals formation of the compounds are ionic character. Why? Because here halogens are highly electronegative elements. Especially fluorine metal halides are more ionic character. So whereas here the ionic character is what happened gradually decreases from fluorine to iodine formation of metal halides. For example, in the magnesium bromide, magnesium chloride, which is more ionic character, magnesium bromide is more ionic character. Aluminum chloride and magnesium bromide, which is more ionic character, magnesium bromide is more ionic character. So that is why it depends upon electronegativity of halogen, the ionic character is gradually decreases children. That is called formation of metal halides. Next here, acts with the halogens. Halogens reacts with the other halogens. So here halogens reacts with other halogens. The formation of the compounds are called interhalogens. So here interhalogens are always more reactive than here elemental halogens. But Fluorine is the elemental halogen is more reactive than other halogens as well as interhalogens also. Whereas your comparison of your halogens and interhalogens, except fluorine, interhalogens are more reactivity children. Why? Because interhalogens are polarity bond. But here only halogens elementals exhibits non-polar bond between halogen and halogen, non-polar. But halogen and other halogen, polar bond. That's why your polar bond is the more reactivity than compared to your elemental halogens, except fluorine, your interhalogens are highly reactivity nature children. So now your interhalogens are formed mainly 4 types of interhalogens. Your general formal representation as X dash. X is one halogen, X dash is another halogen. Here both are here exhibits the ratio 1:1 ratio. That's why X dash. I was given example ClF, BrF, chlorine monofluoride, bromine monofluoride. These both are gas state, but ClF is colorless gas, but bromine chloride is pale brown color gas. But here all this type of XX dash type of structure is linear shape, children. What is the shape? Linear shape. Like that. X dash 3. This is ratio 1:3. Here one halogen combines with 3 other halogens. Example here ClF3, chlorine trichloride, bromine trichloride, iodine trichloride, iodine trichloride. I was given different examples. Here different colors as well as physical states also. Your ClF3 is a colorless gas, but BrF3 is a yellowish green liquid. IF3 is a yellow powder, but iodine chloride is a orange solid, orange color solid state. But this type of halides, trihalides, their shape is a bent T shape. Bent T shape. Bent T shape means children like this shape. Here contains as X halogen, taken as here this halogen and this halogen. Here this is about the formation of here. This is X dash, here X dash, here X dash. But here and here consisting of lone pair of electrons. So means here undergoes hybridization also. Here sp3d hybridization for XXD type of halides. Next, X dash for here examples are here iodine pentafluoride, bromine pentafluoride. Here BrF5 and here ClF5. It is ClF5 also. Fluorine pentafluoride. Here first one is colorless gas, next two are your colorless liquids children. Here all our shapes are square pyramidal shape. That means here it undergoes hybridization is sp3 D2 hybridization children. What is here? sp3 D2 hybridization. Yes, so here like this X dash, here X dash, X dash, here X dash, here one more X dash, but contains only one lone pair of electron. Only one lone pair of electron children. It undergoes sp3 D2 hybridization. Then the last one is about here XX dash. That means here one halogen combines with 7 halogens. The best example is here iodine heptafluoride. It is a colorless gas. It is a shape is a pentagonal bipyramidal children. Pentagonal bipyramidal. So in pentagonal bipyramidal, so then here the shape is like this children. Here next here pentagonal bipyramidal. Example we take iodine, fluorine, fluorine, fluorine. Yeah, one of the question of base goes by pentagonal bipyramidal. It undergoes hybridization of sp3 D3 hybridization. There is no lone pair of electrons. All are bond pair of electrons. Hydroxide undergoes sp3d3 hybridization. Yeah. Also, how many chlorines? 7 chlorines. 1, 2, 3, 4, 5, 6, 7 chlorines. Pentagonal, bigonal. So now you have to circle here. What happened in XX type of compounds? V F shape. So X dash type of compounds, T shape. It undergoes hybridization, sp3d. X dash shapes are here, square pyramidal. Hybridization is sp3d2. X dash 7 here. Pentagonal bipyramidal hybridization is here, sp3d3 hybridization children. So these are various types of interhalogen compounds.